All right. Yeah. So, yes, no. 2 days ago, welcome, period 7 and the internet. Talking about calculus. In particular, we're talking about fluents. What is a fluent? A variable which depends on time. A flexion. A flexion is the sort of instantaneous speed of that fluent. And we're talking about moments. The moment of any fluent is the amount by which it increases in some infinitely small period of time. And what Newton does is he uses, for his infinitely small period of time, this little symbol O. If we have some fluent x in some infinitesimal time period O, then x dot O is the speed at which that fluid changes, the flexion, times the infinitesimal amount of time. That's the infinitesimal change in that fluid. Cool? Cool. All right. And this is what he says. These are direct quotes. He wrote, I believe, in English, not Latin, these books, these papers of his. Well, yeah, this is exactly what we did yesterday. You can read this yourself. I don't need to say it out loud. And then this phrase which he used, I think this was the last thing we did on Wednesday, was he says, since O is infinitely small, terms which have it as a factor will be equivalent to nothing in respect of the others. I therefore cast them out. This is his justification for blowing off the terms with infinitesimals in them. Okay, so this is, I think we got a good taste of Newton's calculus on Wednesday. Let's just get a kind of capture all the various things he could do with this. Well, or rather, we've seen how he finds the sort of slope of the tangent line. This is how he solves kind of the other problem of calculus, to find the distance or the position change given the velocity. Well, this is, as we know from analysis 1a, this is just finding the area under a curve. Everyone kind of already knew how to do this, or rather I should say Fermat knew how to do this, and Newton was aware of these works for polynomials. And for non-polynomials, Newton just used the power series. The FTC, what we made such a big deal of in analysis 1a, was considered by Newton to be essentially just trivial and self-evident. And the idea goes something like this. Okay, a curve is generated by the motions of x and y, and so the flexion of the area was in fact the ordinate multiplied by the flexion of the abscissa. Okay, let me try to draw this. So the idea is you have some curve, and okay, the curve is like this. This is very similar to the casual proof of the FTC that I probably gave you in analysis 1a. So says Newton, if a point x comma y on this curve, think of a fluent x and a fluent y, and let z be the fluent which represents the area of this curve. Well, then, what is the infinitesimal change in z? What is the rate at which z is changing? Well, the rate at which z is changing is just whatever the y-coordinate is times the rate at which x is changing. So this is this like very, can someone make sure that I'm like in frame and stuff? What we have here is this point x comma y, and then x dot. Okay, we're sort of thinking of, this is really not kind of a perfect picture, because the change in x would in fact be like O x dot. But really it's actually even more casual than that. It's just like the rate at which the area changes is just the y-coordinate times the rate at which the x is changing. Because in some tiny period of time, all you're going to get is some new little rectangle. And if that's true, well, then by dividing both sides, you get that the rate of change of the area with respect to the rate of change of the x is just the y. And that's just the fundamental theorem of calculus, that the derivative of the integral of a function is just that function. So I'm going to write it out in like more normal language, or does everyone kind of get it?
Good.
Okay, good. Woo! Wow. Okay, one reason, I think I said this on Wednesday, one reason why Newton doesn't, it has been speculated that one reason why he doesn't publish these papers formally is because he's not quite satisfied, and he continues to work and rework the basics in these 3 different papers. So he got the whole idea basically in a period of like a year, but then he continued to sort of work on it over the remaining decades. And in particular, people got mad. People initially were just bewildered by all these fluxions and fluids. He had new notations. It was this whole kind of bewildering world of calculus. And people protested, like, well, what the hell is a fluxion? Like, can you just explain this? And people didn't understand this thing, how he was sometimes treating it as infinitely small enough that you could ignore it and sometimes not. And so he got like kind of defensive. And so here are, over a period of decades, some different answers to what Newton gave to like what is a fluxion actually. And he says, okay, here's the first answer. Fluxions are, as near as we please, note the echoes of like as close as you want kind of thing, which we have in the modern definition. The increments of fluids generated in times equal and as small as possible, and to speak accurately, they are in the prime ratio of nascent increments. All right, that means absolutely nothing to me at all. That's basically terrible. Okay, next. What are ultimate ratios? This is now, you talk about like derivatives, right? And these ultimate ratios are in which quantities vanish, are not, strictly speaking, ratios of ultimate quantities, but limits to which the ratios of these quantities, decreasing without limit, approach, and which, though they can come nearer than any given different whatever, they can neither pass over nor attain before the quantities have diminished indefinitely. What is he talking about? Does anyone know? I know.
Is it the definition of a derivative?
Yeah, these are just derivatives, right? He's saying basically that if you have some curve and you want to know the slope of the tangent line to the curve at some point, then you pick a point which is a little bit more, and then you sort of, what you do is you find the change in x and the change in y. This is how we're doing now, right? And then that change in y over change in x becomes infinitely small as this point moves infinitely close to a, yeah? Or maybe just call this x. Okay, and so what he's saying is ultimate ratios, the ultimate, so-called ultimate ratio, is the ratio between the infinitesimal change in y and the infinitesimal change in x. In other words, it's the ratio that exists after the point is like all the way to a, or something like that, right? It's basically the derivative. It's the slope of the tangent line. But when the point is already all the way there, he calls it the ultimate ratio. And he's saying, and what are these quantities which are vanishing? The quantities which are vanishing are the delta x and delta y, because after all, is everyone with me? When you get all the way there, the actual change in x and the change in y do in fact vanish. And so he's like, kind of like wants it both ways. He's like, well, yes, these quantities are vanishing, and I have an ultimate ratio, but the ultimate ratio I have is like between nothing and nothing, so that doesn't really make any sense. So he's like, okay, strictly speaking, these ratios of these aren't really ratios of ultimate quantities. It's not a ratio of 0 to 0, but it's like limits. So they're just mumble, like it's all just going around in circles. Okay, this is like a hot mess. More. Voice is going away. Now he says, perhaps it may be objected that there is no ultimate ratio of evanescent quantities. Yeah, I do object to that. Because the ratio before the quantities have vanished is not ultimate, true. And when they have vanished, it is none, also true. But by the same argument, it might well as be maintained that there is no ultimate velocity of a body arriving in a certain place. Okay, so here he argues that, yes, this is kind of on the face of it incoherent, but so is the very concept of instantaneous velocity incoherent, if you think about it. But yeah, we seem to be okay with that. So, like, you know, it's just kind of like that, man. Do you see how the physics is sort of wrapped up in the calculus? Okay, good. This is now a new quote. The ultimate ratios are not actually ratios of ultimate quantities, but limits which they can approach so closely that their difference is less than any given quantity. All right, already Newton, this guy is very, very smart. He's already realizing that, like, somehow what he really means is not that it equals this, but it can be as close to it as you might wish. Okay, all right. These are basically like, what is this? This is like epsilon delta, right? Coming soon. Okay, before we get to epsilon delta, let's talk about the other guy. The other guy is Leibniz. Leibniz, a totally, completely different kind of person in every way. He is German. I can't remember his exact biographical detail. He doesn't actually learn any math at all until he's like 24 or something like that. Hold on. He has created calculus basically completely independently of Newton, although that's a little controversial. He did it really all like about 15 years later. He also did all kinds of other stuff. He was this basically kind of a philosopher. And let's see, let me see what's on the side. Between his work of philosophy and logic and his day job as a politician, he also decided to work on mathematics. I can't remember the exact story, but I think at some point he is talking to some other person, like Christian Huygens or something like that, or one of these other kind of people of that era, and they say, hey Leibniz, you should probably learn some math. And Leibniz says, okay, that's good, I don't know any math. Can you lend me some books? And pretty much in a period of like a year or two, he reads Euclid, he reads all of Descartes' geometry, and he reads like Vieta and all those other major works, and then suddenly he's just like in the game. And he starts, he comes up basically completely independently of Newton, his own system of calculus, which is the exact same thing. And this gets very controversial later because Newton claims that Leibniz actually stole all of this from him. Okay, more on that in a minute. All right, what does Leibniz do? Leibniz does something totally, okay, here's Pascal's triangle. I'm not going to talk about that. We all know this already. Yeah? Oh, you should turn in your packet, if you have it out, to page 5. Pascal, or rather Leibniz, and maybe someone should turn the video over here. Leibniz is messing around with Pascal's triangle. What does Pascal's triangle look like? If you have the packet, it would be nice because I've written it in a certain particular way, which is the way that Leibniz wrote it. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4. What is that? 6, 4. Yeah. 1, 1, 5, 10, 10, 5. Let's do one more. 1, 6, 16, 20. Okay. So, good. This Leibniz calls the arithmetic triangle. It's just Pascal, what we now call Pascal's triangle, but actually the Chinese and the Arabs had this 1,000 years before Pascal. Okay. Leibniz investigates the so-called harmonic triangle. I do not think he invented the harmonic triangle. I think it was around. So what is the harmonic triangle? You've probably never heard of it. It goes like this. The harmonic triangle, it's on your paper, is formed by dividing, so first we seed it, just to make sure I explain this correctly, with the reciprocals of the positive integers. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. Okay, and now to create column 2 of the harmonic triangle, we divide column 1 of the harmonic triangle by column 2 of Pascal's triangle. Okay, so, and we indent in 1. So the thing that goes here is that number, if I'm doing this correctly, column 2 of the harmonic triangle is formed by dividing column 1 of the harmonic triangle by column 2 of Pascal's triangle.
Yes.
Yeah. So this is column 2 of Pascal's triangle. This is column 1. So I now divide these or something, right?
Yeah.
Why am I not getting what I want out of it?
1/2 by 1. Yeah, you do. Yeah. 1/3 by. Yeah.
Yeah, so
I
1/2
divide 1/2 by. Oh yeah, done. Okay, so I divide 1/2. So here we just leave it blank or something, right?
Yeah.
So I divide 1/2 by 1, and I get 1/2. I divide 1/3 by 2, and I get 1/6. I divide 1/4 by 3, and I get 1/12. I divide
20th.
what was that? I lost track. 1/5 by 4 and get 1/20th. I divide 1/6 by 5 and get 1/30th. And I divide 1/7 by 6 and I get 1/42. Cool? Okay, subsequent columns are generated similarly. Now I divide column 1 of the harmonic triangle by column 3 of Pascal's triangle. Let's do one more of these together. So now if I divide, so wait, am I having so much trouble with this? Column 3 of the harmonic triangle is formed by dividing column 1 of the harmonic triangle by column 3 of Pascal's triangle.
So 1 over.
So I just start here. That's the part I messed up. Yes.
When you say like for any element with row number.
Yeah, wait. I am too sick to do this precisely. Do you get it?
Yeah.
Okay, good. Woo! So I start with 1/3, and I just do 1/3 divided by 1. 1/4 divided by 3. Hopefully, 1/5 divided by 6. 1/6 divided by 10. And finally, 1/7 divided by 15. So it's going to be 1 over 1/5. Okay. And then the rest of the yo.
I think it's more intuitive to think of it as dividing rows, because you're like, instead of like having like infinitely long columns, you're like building Pascal's triangle in the same way that you're like building
you
by
take the
addition
first
by
column
rows.
and you divide it by each number like in that row of Pascal's triangle. So like 1/3 is in the 3rd row.
Oh.
Yeah, for
and
any
then like you divide it by each number in the 3rd row of Pascal's triangle.
You guess what Adam was trying to say when he cut off. Wait, say it one more time, Ambrose.
Okay, so like you take the first, so you list out like the harmonic numbers. Like 1, 1/2, yeah. And then so you take, if you're going to like the 4th row, you're say 1/4. You just divide it by each one.
Oh,
in
so
the 4th
just go row by row.
Yeah.
I see what you're saying.
Yeah.
Okay, so so start with a half and just divide by 1/1.
Correct.
Then start with a 1/3 and just divide it by 1/2.
Yeah.
Okay, that's better. That's just smoother. Yeah, good. I like it. Woo, good. Well, so what? Here's a fact about the harmonic triangle. Any entry in the harmonic triangle is the difference of the two numbers in the previous column. This is not obviously true, but if you subtract 1/6 from 1/2, you get a 1/3. If you subtract a 12th from a 6th, you get a 12th. If you subtract a 20th from a 12th, you get a 30th. If you subtract a 30th from a 20th, you get 60. And if you subtract a 42nd from a 30th, you get a 1/05th. You can just trust me on that, or you can verify it. I'll post the answer key to this packet eventually, and I have written out the precise combinatorial identity which one must prove to verify that this is true, and you can just knock yourself out proving it if you want to. Okay, so what is the big idea? Well, what Leibniz does is he starts to have some fun. He says, okay, this is the part that gets kind of deep and interesting. What we shall now do is recognize that this is a sequence of differences. And if this is a sequence of differences, then what I can do, for example, is represent the difference between 1/2 and 1/42 as a sum of a bunch of differences. In other words, he says, okay, what's 1/2 minus 1/42? Well, 1/2 minus 1/42 is just going to be 1/2 minus a 6th plus a 6th minus a 12th plus a 12th minus a 20th. You guys with me?
Yeah.
Plus a 20th minus a 30th plus a 30th minus a 42nd. But, of course, that's what the next column of the harmonic triangle represents. This is just 1/3 plus 1/12th plus 1/30th plus 1/60th plus 1/25. Okay. So, so what? Well, he now says, look, were I to continue this infinitely often, then this number here is just getting smaller and smaller and smaller. And so he then says with a kind of, whatever, 1/2 just basically is, and he just presents this infinite series, 1/3 plus 1/12 plus 1/30th plus 1/60th plus 1/1/5. In other words, he creates sort of from this concept of differences, he creates these sort of infinite series. And the idea here, the big idea of Leibniz, is that if you want the difference between two things, you can just sum up a series of things composed of those small differences. All right, this is revolutionary because he now extends this to arbitrary summation problems. Can I erase this? Yeah, I guess got what you need out of this. Okay. So I think this is brilliant, and I might just change your whole concept of calculus in the next 5 minutes. He says, Leibniz, that, well, consider some curve. I'm on like the last page of this packet now. Consider some curve. And let's just start at 0, 0, because that's what Leibniz always does. Okay, so here's some curve. Well, let's consider this curve as being composed of an infinite number of little pieces. And make sure I'm doing this correctly. So yeah, so this is like x1, x2, x3, x4, x5, x6, etc. Okay. Now, let these be the corresponding y values. So these are the heights. These y values I'm writing are the heights, the ordinates, as you would say, I guess. Okay, and so now he says, well, take the following sequence, the sequence of differences, and he has some notation for this. His notation is delta y sub I. Okay. This he calls the sequence of differences. Well, what does this sequence look like? It's the sequence which is like y1 minus y0, so it's like y1. And then the next term in the sequence is y2 minus y1. And the next term in the sequence is y3 minus y2, etc. Everyone get it? Okay. Okay, whatever. Okay. So, and it ends with, let's just, if we're doing this in general, then it ends with like y, maybe I should kind of go, like, let's I sort of went too far here. Let's just call this xn, and let's just call this like yn. Okay. And so it's going to end with, so dot, 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 it's going to end with yn minus yn minus y. Okay, well, this is a sequence of differences. What happens if I sum all these differences? So, yeah, take the sum over all the i's of the sequence composed of the differences in the y values. Then, of course, what do you get? Yn minus y0, right? Because, as someone just said, it telescopes. Plus, you can just see visually, right? You add the difference, plus you add the difference, plus you add the difference, plus you add the difference all the way over, then what you get is the total change, right? In other words, Leibniz just gets very confident with himself that if you add up an infinite number of tiny differences, what you get is like the total length of the segment, so to speak. Okay? Or the arc, or whatever it is you're adding. Okay, now alternatively, consider the sequence of partial sums. Okay, sequence of partial sums. All right, this he writes with this new notation that he comes up with, delta y sub I, and he says, so think of this as like a sequence. And okay, what does it mean to take the sum? What does it mean to take a partial sum? Well, it's just going to be the sum of all the things like up to that point, like, as you guys know. Okay, up to the ith y value. Okay, well, now if I have some sequence, I can always construct the sequence of partial sums. Now Leibniz thinks of these two as like operations or something, and what is the difference? then he creates this new thing called the difference sequence. So the difference, so this one actually he already has this. So there's sort of two things here. There's the sequence of differences and there's the sequence of partial sums. But they clearly have some kind of relationship, right? Because if you apply the sort of difference operator to the sequence of partial sums, then this is just the sequence of differences in the partial sums. And what is the sequence of differences of the partial sums? Wait, okay, so in other words,
Oh, it's just the last two.
it's just the sequence back again, right? Hold on, I am doing a crappy job of explaining this. Take a sequence, like a sequence of y values, right? Now, consider the sequence of partial sums. What does that sequence look like? So I'll just write this. I'll write it like this. This is a sequence, so to speak. Let's just call that a sequence. To Leibniz, this is y1, comma, y1 plus y2, comma, y1 plus y2 plus y3, etc. With me now? Say yes.
Yes.
Woo! And that is that's a sequence of partial sums. But now, take the differences of this sequence of partial sums. So now apply the sort of difference operator to this sequence, and what do you get?
Y plus 1.
Well, now you're getting the difference between these two. Oh no, I guess I need to start at 0, right? Let's do it that way.
Yeah, wait, if you start at 0,
Then it's like better.
then it's the.
Then it gives me what I want.
Otherwise, you get like.
Sorry, that was maybe a little bit confusing. Yeah, so start at 0, but y0 is sort of always 0. That's why we kind of left that one off. But what's the difference between this? What's the difference between y0 and y0 plus y1? Well, it's y1. What's the difference between? Now I need all these y0s in there, but I don't want them there because they're all 0, right? I'm just going to leave them off. So what's the difference between y1 and y1 plus y2? y2. What's the difference between y1 plus y2 and y1 plus y2 plus y3? It's y3. Okay, and so what's happened here is Leibniz has created these two operations. Given any sequence whatsoever, he has this new operator, so to speak, which creates a new sequence. This is the sequence of differences. You guys following this?
Follow.
And given any arbitrary sequence, he creates a new sequence called the sequence of partial sums. And then he just very liberally applies these concepts to all kinds of things. And what we have seen already, and he makes this observation, that these two operations are clearly inverses of each other. So, for example, I'll just repeat the two things I already said, right? If I take the sum of all the small little differences, then what I get is the total difference between the first and last term of the sequence, right? So the sum of the differences is the total change in the object, and furthermore, the other one, the sequence of the sequence of differences of the partial sums is just the original sequence back again. Who's following all this? Okay.
All of
Woo! So now he says, okay, well now let the differences be infinitely small. Is the camera still following? So now, once he moves on to infinity, he invents a new symbol. He's like, okay, this summation is too discrete. I need to add up an infinite number of things. So he creates this integral symbol. Leibniz is doing this. And he says, okay, what happens when I take the sum of an infinite number of tiny little differences? Well, what I get then is the total thing, right? And he thinks of this as like a line segment. Imagine that this is effectively like a line segment whose length is like y, right? And what he's doing is kind of partitioning up that line segment up into an infinite, and taking all the tiny infinite number of differences, is how Leibniz thought about it. If you sum up the infinite number, if you take the infinite sum of these infinitely small differences, then you just get the total length back again. Cool? Okay? But then, so that's like point one. But then he says, okay, well, what happens when I apply my sort of principle that these are opposites of each other to the infinite case? Well, what does it mean to take infinitely small differences of the sum of an infinite number of things? He wants this to make sense, but he doesn't know what this means. Right? It's unclear what this should mean. Because how can, says Leibniz, you ever sum up an infinite number of things? You can't do that. So he changes the problem slightly, and he says, okay, instead of this being y, let it be like y dx. In other words, he says, okay, let me not sum up an infinite number of y's, let me sum up something, let me take the differences of the sums of the form y dx. And this is y dx. In other words, his principle of his principle here that the differences in the sequences of partial sums gives you the old sequence back again, he applies to the product of y and some small change in x. And what this is basically saying is, this is basically the fundamental theorem of calculus, right? What this says is, if you have, well, in words, what this says is, the infinitesimally small change in the total area under the curve is just the infinitely small change, is just the infinitely small area at that point where you're making the change. In other words, if you think of the things to be added as not y's, but little tiny y dx's, right? If these are the things that you're adding, so in other words, construct a sort of sequence of these rectangles, add up the infinite number of those tiny infinitely small rectangles, that to him makes sense. Then if you take the differences in the partial sums, then what that's going to give you is the rectangle that you just added. This is the fundamental theorem of calculus, right? This is dx, this is y, and at any moment, the change in the sum so far is just the last one that you just did. All right. So he, in his own kind of way, finds the FTC to be just totally trivial and obvious. And he sort of thinks, he's sort of less, I don't know, this, to me, I think this is kind of fascinating. This is a completely different approach than Newton has taken. This is more of a kind of series sort of approach. And it's there's all sorts of, people have looked into this.